thank you for this day and for your loving kindness. Thank you for blessing our lives together. You can do that, and you do it, and we don't even know that you're about it. But I thank you, Father, and pray your blessing on this class. For Cole, who's sick, you know about him and why, what's going on in his body, and I pray that you would minister a special measure of grace to him. Just do something that he'd recognize is from God. I do pray your blessing on us here this afternoon. You would guide and direct this time in a way that works for good in Jesus' name. Amen. Okay, so I'm going to just run through this kind of briefly. This is number 11, and some of you. So if you quote something and you don't know what it means, and I'd say the percentage of people that quoted stuff, long paragraphs of stuff, I don't know if you know what it means or not, but from experience, I'd say if you're quoting a piece that's this long, and the answer is really a sentence, that you probably missed something. Okay? So if you look at it, I passed out, I did all the lemons that I had, so I should have passed out yours. So summarize the process by which water changes from one state of matter to another. This next line, I don't know how many people, both here in the async class, didn't get this one. Indicate whether heat energy is absorbed or liberated. That should be a clue. To go to a paragraph about bond breaking is fine. It was true. But the question wanted something like this, very simple. When ice changes to water and water to water vapor, latent heat is added or absorbed. When water vapor is cooled to form water and cooled further to form ice, latent heat is released, liberated. Okay, now I didn't ask for the words, well I did. Absorbed or liberated. Absorbed, liberated, or released. But that's a simple. I mean, if you're looking at your paper and you have a paragraph about bonds breaking, it's true, but this should be an indicator that if you didn't mention this, then you didn't get the question. So either you should ask, if you get bonds broken, a paragraph, and you don't see this, and you say, well, Mr. Nelson, what's the deal? I talked about bonds here for a whole paragraph, but you're asking about something else. What are you asking for? I'd answer you, and I'd be happy to. It wouldn't be an imposition. I wouldn't be thinking, oh no, it's one of my students or their science, I don't want to do this. No, that's not it at all. I'm happy to do it. So if you have questions, if you ask me, I'll be happy to answer you. In that way, I'd be kind of like Jesus. If you have questions, real questions, and you ask him, the chances are he's going to give you some direction or answer. It may not be what you're looking for, but it'll be genuine and it'll be what you need. He does it every time. So, what happens when air is saturated? This, again, very simple. The maximum quantity of water vapor that the air can hold at any given temperature and pressure. So saturated air is air that is full of water vapor, can't hold any more. If it gets more, if you add more into it, or if you cool it and it can't hold any more, it has to do something with it. And so it condenses. It becomes clouds. It becomes water vapor. Well, it is water vapor. It becomes clouds. If you have saturated air, which is full of water vapor, it can't hold any more if it's saturated. Saturated means full of. If it's not saturated, then you could still add some to it and it wouldn't condense. You wouldn't see a cloud. You wouldn't know. You could look at it all day long and think, oh, well, I don't see anything there, because nothing's happening. But if you add water to where it's saturated, it can't hold anymore, and you continue to add water or cool it, either one, you can add water vapor to it, or you can cool it, but it'll come to a point where it can't hold it anymore, and so it'll get rid of what excess it has, which is, it's gonna condense. So after studying the table on 17.1, page 521, write a generalization. So that's a generalization. Write something generally about this table. Well, all you had to say is, the higher the temperature, the more water vapor the air can hold. That's it. That was good enough. You got full credit if you answered that way. It's very simple. That whole little table says the higher the temperature, the more water vapor the air can hold. Conversely, the lower temperature, the less it can hold. The less water vapor it can hold before it condenses. There's a maximum. I mean, I went to Subway, or went to, wherever it is, Showtime. So I didn't get a tan, because I read about that and I just, no tan today. So, ordered, so I got somebody else's meal, but I never ordered what I ordered, so I didn't know what it looked like. And I just got my hamburger, took a bite of it, put it down, and then the guy comes out with he misread the receipt or whatever. So I got to eat what I had first, and I got what I had second. So I got 2 meals for the price of one, in fact, for the price of none, because I was taking out. So that's sweet. But I could only eat so much. If I tried to eat that second burger, I tell you, I would get to a place of saturation. In economics, they call it utility. My first hamburger is great. And the second one may be good. And the third one is fair. But after a while, with enough hamburgers, or hot dogs, or mac and cheese, or anything, you get to a point, and then after that, you get less return from it. And pretty soon you don't want it anymore. I mean, you have so much. There's people that eat hot dogs that eat, I can't believe how many they eat. I don't know what they do with them, but anyway. So that the illustrations always don't hold water. So the amount of water vapor in the air remains unchanged, if it does. So you got water vapor, a certain amount. You don't know how much. It doesn't say it's saturated. It just says you got air with a certain amount of water in it. How does a decrease in temperature affect relative humidity? So you got air, and you got water vapor in the air, and at a certain temperature, and then you reduce the temperature. Well, the ability of the air to hold moisture decreases. So you got more moisture in there, comparatively speaking. The air can only hold so much. If it can hold 50%, if it's 50% full, when it's this hot, and you shrink it so it can't hold as much, then the humidity, relative humidity, will increase because it's a percentage. Relative humidity, not humidity, relative humidity, like your ant humidity. If you had a relative that was humidity, and that means it's a percentage. So you've got well, that's a cloud. I don't want it to be a cloud. I want it to be a package of air. I don't want you to think it's a cloud, because that would be condensing. But if I had just a package of air, and I had so much water vapor in it, water vapor. So, this water vapor in this amount of air, let's say that's, 15% of the total. Here's all the air. You could fill this thing up with water vapor. It would be saturated. If you had water vapor filled this thing, it would be saturated. It'd be 100%. but they'll say this is only 15% of this. But then if I cut this down, if I cool this, so if it's cooled, it's only gonna be like that now. I've reduced the amount that this can hold before it's saturated. So the same amount, that was 15% when it was all of this, is, let's say, 25% now. Because I've shrunk. By cooling it, I've shrunk what it could hold. It can't hold as much. So on a warm summer day, when the relative humidity is high, so high humidity, it may seem even warmer than the thermometer indicates. In other words, why do some tend to feel uncomfortable on this muggy day? I wasn't tight on this. Some of you look at outside sources. You say, I can't find this anywhere, so you Google this question, and it gives you an answer. So that's what happens. So, but matter of fact, if it's high humidity, that means there's a lot of moisture in the air. So if you're doing like I'm doing right now, my body is putting out little teeny beads of perspiration. It's shiny. It's water. And it came right out of me, just as I'm standing before you, huh? It's a miracle. It just appears. Well, it appears, and if there's a lot of moisture in this air, it would appear because God's designed us. So when that's liberated, when it evaporates, we're cooled. My body, it's a mechanism of my body to cool itself. The sweating, and then that evaporates out in the air. Well, when the air is drier, and that happens, it does it quicker. But when the air is really full of moisture, it doesn't do it as effectively. It doesn't mean you don't sweat, but it doesn't leave your body as effectively as it does. I mean, you could buy clothing that helps to wick your body, like runners and probably football. I don't know who's wearing all this stuff, but they're wearing stuff that helps to act like a wick. So you sweat, and it accelerates the moisture to leave your body, which provides cooling. But warm temperatures allow the air to hold moisture. That's why it's not saturated in this case. It could be, but it might not be. When relative humidity is high on warm days, it means that a lot of moisture is being held in the air, which produces a muggy, sticky kind of day. The air seems thicker and the heat more oppressive. It might be one temperature, but it feels like Josiah Martin. So where he's from, I remember driving a group of students from Virginia Tech down to Tuskegee, the Tuskegee Institute. So we were in a van with 2 tanks of gas, had double tanks. So you could should be driving, when one gets low, you just switch over to the other one and then you keep on going. So we drove a long way, and we got down to Mississippi to get some gas. So we've been driving in AC, just fine, very comfortable. I opened the door of that van at the gas station, and it's like the heat just slapped me. I mean, it was hot and humid. And if you think there's kudzu here, you know, you see forests that are just like somebody put their quilt, their green quilt over the whole forest. It's something. But it was hot and humid, and it was really it felt, I'm sure, a lot harder than it might have been. So most of this, if you note, most of these answers were pretty short. I mean, I'm not going to ask you a question like the first one and expect you to write a paragraph on bonds breaking. I mean, breaking of bonds it's a real reaction. It really happens. But to memorize that much material, I'm not going to ask you to do that. But I'm expecting you to know something like this. Now, The last one that was required, and I think it said something else, has a different, I think it said something about be specific and scientific. But I wanted a thought out answer about what really went on. So that was maybe my mistake in not making it clear enough. But this was worth 8 points, because I thought there were at least 4 parts to this worth a couple points. So the air around the cold bottle, you take a bottle of Ale-8 out of the fridge, the air around that bottle is colder than the warm air surrounding it. Because this, I say, it's a hot summer day, so it's warm. So you have a cold bottle you take out of the refrigerator, and it doesn't have any condensation on it, it's in the reefer. So you pull it out, and you set it down, and immediately this thing starts to perspire. Well, it's not sweating like I do, or you do, but because the air around that bottle, right immediately close to it, is really cold, and it can't hold much moisture. But the air around it holds a lot of moisture. So that air around it that's carrying all this moisture gets close to this bottle, and it has to condense, because the air that's around it is holding more than it can if it's right next to that bottle. And so the air around it condenses. It gets wet on the bottle. So the moisture air coming in contact with the cool air surrounding the bottle, because it doesn't have the ability to hold as much water, the excess starts to condense on the bottle. And so this, nobody put this down anyway, but implicitly this phenomenon makes it look and taste even better. There's just something about a cold, condensed bottle with condensation on it, just makes it. Anyway, so I had these things. I probably won't test you out. I might, but I'm not probably going to. Okay. Extra credit. Contents of an aerosol can are under very high pressure. When you push the nozzle of such a can, the spray feels cold. Explain it. Air is moving from high pressure. It's in the can. It's under high pressure. You press on that, and it shoots out, and immediately it's going from high pressure to low pressure. So it's expanding. This pressurized air goes, and when it expands, it cools. And expands real quickly. Air that is expanding because reduced air pressure cools. You can read about that with the adiabatic stuff. And I just want to note, reading this stuff to answer these questions is one thing, reading it to understand it is another. Like you can read the Bible as a novel, you can just read through it and not think about it, you just read the story. Or you can read it and be asking yourself, what does this mean? How does this work? Why would he say this? Why would she do this? You can ask yourself questions and dig out something from it. Well, if you read this book, I doubt whether anybody's going to read it too much like a novel, but if you read it to answer your questions, because you got these test questions, but that's all you're doing. You're just looking for the answer. So you got a keyword, okay, where is bottle? Bottle, okay, quote, cut and paste, there we go. Well, you're probably not learning, and if we were England, you would get a test at the end that would be over everything. It would be a final. It would be like, wow, everything. And you'd have to remember from the first part of the semester, and the second part of the semester, and the third part of the semester, and the last part of the semester, and you would have to know it all. Well, in this class, I'm not requiring you to do that. Your final may have some stuff on creation, but when it does, before next week or by next week, I will tell you what you need to have in your mind if I'm going to do that. Otherwise, what you're going to get is this section. And this is the last section. It's got a lot of information. So, air is moving from high pressure to low pressure, and you found, if you read about, some of you did, because some of you did talk about this moving adiabatically. Either you had read it, you got it in high school, or you read it or got it by reading the book, because that's what happened. Air expands, it cools. Rapid expanding air rapidly cools, hence you got a cool feeling. Okay, so that was it. That was it. If you have questions on this, I would be welcome to see you after class. Let me see, do I have? Okay. So we're gonna finish up this one thing, hopefully, quickly, and then stop here. So I didn't go over, I just started to go over this little piece. Did you get one of these, Anthony? Do you have changes of state?
I think so.
I didn't just hand it up to you. Oh, but you do?
He doesn't.
Oh, he did?
He doesn't.
Oh,
Yeah,
that's
you weren't here, yeah. Okay, so it's on the second or third page back. Okay, this says, this is a temperature, so you can see the temperature goes from 32 to 68 to 86. And this is the relative humidity. And this is how much water vapor per cubic meter. So you got almost 5 grams per cubic meter of water vapor. Well, 32 degrees, that's saturated, that's 100%, can't hold any more. If you put any more water vapor in this 32 degree air over this, it's 4.85. If you put 5.0, so you'd be putting 0.15 grams per meter cubed of more water vapor in here, it would start condensing. It would start making clouds. But if it was 43 degrees, it's only 67% relative humidity. 52, 36. So at 86 degrees, this amount of air, this amount of water vapor in the air will only give you 16% relative humidity. It'd be dry air, feel like it was dry. That's because increasing temperatures decrease relative humidity. So you can follow this, I hope. This is 100% saturated, you got 7 point. So I could raise this to 7.27 grams per meter cubed, and it would saturate at this level. At 43 degrees, it'd be 100%. Saturated. Put any more in, it would start condensing. Same here, you can get even more, because it's hotter. And even hotter, and even hotter. And here, at 86 degrees Fahrenheit, you could have 30.4 grams per cubic meter of water vapor before it got saturated. If you took this much water vapor and put it in this, the difference between 30.4 and 17.31 would result, that all be condensed out, because it can only hold 17.31 grams. If you go down to 68, that's all it can hold. So you could have this much, but it condensed out, so it would be only holding that. The rest would be condensation. On a cold winter day, relative humidity 100%. Well, you see, okay. Seems drier than a summer day with relative humidity that's lower because it can hold more water. There's more moisture in the air on a warm day than a cold one, over 3 times as much. That's the comparison of that thing if you look on your sheet. How relative humidity changes. That might be something you should know. How does relative humidity change? If you change the temperature or the moisture content. If you increase or decrease the heat, it will change things. And if you increase or decrease the amount of water vapor in there, it'll change things. So, like evaporation from a lake raises the moisture content of the air. It evaporates the moisture content, water vapor. It goes from a liquid in a lake, it evaporates and becomes a gas. So as it goes from a liquid to a gas, you get more moisture, more water vapor in the air. We'll find that as we talk about tropical storms and those things that come across the water, especially like the Gulf of Mexico and that, they come off the Atlantic, and that water, sometimes that water gets really warm and then it's evaporating like crazy. And the mechanism for generating tropical storms, hurricanes and the rest of them is just feeding on that evaporated water. It really likes it. It tastes good for it. So condensation, so saturated air, if saturated air at 86 degrees is cooled to 68, we'll have 17.31 grams per meter cubed of water vapor in the saturated state. However, if we started with 30.4, then what happened to the other 13.1? It condensed into a liquid, resulting in the generation of three possibilities: dew, fog, or clouds. That's going to happen. When the air gets saturated, it's going to condense what it can't hold, and it's going to happen to end up as dew, fog, or clouds. Any form of condensation, for any form of condensation to occur, the air must be saturated, and saturation occurs when either the air is cooled to its dew point or water vapor is added to the air. Also, there generally must be a surface on which the water vapor may condense. And the surface doesn't have to mean grass on the ground, it could be little particles in the air. Dew is things on or near the ground provide the surface. Above ground, fog or clouds need condensation nuclei or hygroscopic nuclei as the surfaces. They need something to land on. Condensation nuclei is little dust, smoke, or salt particles. A lot of them down below where we live. We're breathing them in all the time. And hygroscopic nuclei are salt particles from the ocean. It is possible for clouds to form without these nuclei, but for that to happen, relative humidity must be well over 100%. So, now, I'm going to move now into air packages. Okay, we're going to look at packages of air within the greater atmosphere. Truth is, it's all air, but for our purposes, I mean, the air is everywhere. So when we think of packages of air, we're doing that just to visualize what happens. Things aren't neatly packaged. There's no definition, there's no demarcation of one border to another. However, we need to think of an area of atmosphere with a given environmental lapse rate, general temperature and pressure gradients. So as you rise in the air, in fact, I think this little picture that I drew myself with all these things. If you see a normal lapse rate, which says 6.5 degrees Celsius per 1,000 meters, it means that if you are starting at zero and it's 30 degrees Celsius at zero, and you go 1,000 meters in the air up to an elevation of 1,000, rather than 30 degrees Celsius, it would be 23.5 degrees. It would lose 6.5 degrees as it rose. as it rose, it would lose that. That's the normal lapse rate, not the adiabatic rate, that's something else, but the normal lapse rate, or the environmental lapse rate. Okay, so we've got this package of air, and we've got a couple of values, got the vapor content of it, and its temperature. So that's what we're gonna look at. We will look at unique air package and see how it interacts with the surrounding atmosphere. We'll discuss how different packages of air act upon each other, but still within the greater atmosphere, which has properties of its own.
Can you go back up?
So, adiabatic temperature changes. These are the result of air pressure. When air rises, just like we talked about earlier, at sea level, the air pressure is 14.7 pounds per square inch. So you have a square inch. And if you took that square inch and took it up 60 miles, a square inch 60 miles high, you would have approximately 14.7 pounds. That's how much it would weigh, because of the molecules in it. They have a weight. Gravity, working on them, is a weight. So that's at sea level. If you go up to Denver, the pressure's less, you've got 12.1 pounds per square inch. Or cubic inch, I guess. Because it's higher, there's not as much air pressure there. Air pressure gets lower the higher you go. When we talked about Mount Everest, you got up to where it was 5 point something and then even 4 point something. I don't know, I don't remember what the top of Mount Everest was, but it was 5 point something pounds per square inch. I mean, it's a third of what it is at sea level. So air is very thin there. But when you increase in altitude, the pressure is less. That's why those balloons that the Weather Service sent up, they get them pumped up so they'll rise, but as they start going up, they continue to expand. Because the air pressures, there's not the pressure holding the air in, and so you have a balloon that expands, and they're designed to do that. And they go up to a certain elevation, and then they burst. And then they come down, and they've taken records of stuff as they go up. I don't know if they do get down, but however, well, they probably are recording something. But then a parachute comes out, and it lets it back to Earth. Hopefully it doesn't hit cow. So, adiabatic change, okay, adiabatic temperature changes. You need to know this, it's a result of air pressure. These result when air is compressed or allowed to expand. So you have expansion and compression. When air expands, it cools. When it contracts, it heats up. So, the dry adiabatic rate, this is a dry rate. And this, from this, no condensation here, but what this shows, if you have an air particle that's 30 degrees Celsius and it increases 1,000 meters into the air, it cools, or it cools 10 degrees Celsius. And if it goes another 1,000, it cools another 10 degrees Celsius. And if it went up another 1,000 to 3,000 meters, it'd be down to 0 degrees Celsius. And if it went up to 4,000, it would be onto -10. The relationship for the dry adiabatic rate. Dry is no saturation. The air is dry, it's not saturated. It doesn't reach to a point of condensation. No clouds, just it keeps rising and you're fine. And the dry adiabatic rate is for every 1,000 meters, it decreases in temperature, then it goes up. Going up, it decreases, coming down, it increases. If you were to push this air parcel right here down 1,000 meters, it would increase from 10 to 20 degrees centigrade and on there. So it's pressure dependent. Anytime air moves upward, it passes through regions of lower pressure. Pressure declines as you rise upward. As a result, the ascending air expands and cools adiabatically. Descending air comes from under increasingly higher pressures, compresses, and is heated adiabatically. So when it descends, it heats adiabatically because the pressure changes. Pressure increases. The rate of heating and cooling when the air is unsaturated, not 100% relative humidity, is called the dry adiabatic rate. So it's the dry rate until it becomes saturated. And then it's going to change to something called the wet adiabatic rate. The rate of cooling for the wet adiabatic rate is between 5 and 9 degrees. So the dry rate goes up or comes down at 10 degrees for every 1,000 meters. It cools 10 degrees going up, it warms 10 degrees coming down for every 1,000 meters. That's the dry rate. The wet rate can be almost 10, can be 9, well, 9 point something, whatever, anything under 10. It can be close to 10, but not 10, but for our purposes, let's just say between 5 and 9 degrees. And why it does that? Because when the air is saturated, when you've got a lot of moisture in the air, or if it was 9 degrees, you would have more moisture than here. You'd have some moisture, and the more moisture you have, the more heat is going to be generated, latent heat is released, so it retard the cooling. So when the rising air begins to condense, turn from water vapor to liquid. If you remember the little chart, and there's a chart on, well, page 518 to 519, there's a chart that changes state. A little different than the one I showed the other day, but that's what it does. So when air begins rising, when air begins to condense, turns from water vapor to liquid, heat's released. The heat or latent heat released works against the adiabatic process and resultingly slows down the rate of cooling. So cooling is slowed if you got air that's condensing. So the air will continue to cool after condensation begins, but will do it at a slower rate. Cloud formation begins at the condensation level. That's where clouds begin. In one of the questions we had on today's assignment, had that. Yeah, I don't know stuff. Oh, the dew point temperature at condensation level if the dew point temperature of the condensation from something, at what altitude will clouds begin to form? So clouds begin to form at the condensation level. If you would have a cloud, you would have a package of air that would be ascending, rising, rising. You wouldn't see it. It'd just be out there. And if you could watch it, if you could watch it right from the ground, and it would go up and up and up and up and up, and if you could just package it, so you could actually watch this package, it would have no definition until it got to a level where it was cold enough to begin condensing, and you'd begin to see condensation in the form of clouds. It couldn't hold the moisture anymore. It just became, for the amount of moisture that was in it, it would max out, and as it maxed out and kept getting colder, it would begin condensing and forming clouds. So cloud formation begins at the condensation level. That's important to know. The wet rate, the wet adiabatic rate, which means what it changes in saturated air. Now this little diagram shows the dry rate. It starts at 32 degrees, right at the ground level. It goes up 1,000 meters. It loses 10 degrees centigrade. It goes up another 1,000. It loses another 10. It goes down to 12 degrees now. 32 to 22 to 12. It goes another 1,000, and it's down to 2 degrees. So when it's down to 2 degrees, because that's the condensation level. In this diagram, that's not the condensation everywhere, that's just in this diagram. In this diagram, condensation, because it says it right here, condensation level. It tells me. I don't need to ask or figure it out, it tells me just flat out. So there it is, condensation level. After this, this air can't hold any more moisture, but it's still rising. So it's cooling. And as it cools, and it rises when it cools, because of less air pressure, it's got to condense. So that's why we have clouds happening. So in this, you go from 2 degrees to -3. So how many degrees is that? 5, it is. That's important to think about. One day, you'll have a problem. They'll want you to be able to do this. Say it rises, 10, -10, -10, -10, well, goes up 1,000 feet, but it's only -5, because it says this wet rate, there's so much moisture in this air. And guess this, there's a lot of moisture, there's a lot of latent heat, excuse me, released, and so it's causing this air that was rising and losing 10 degrees every 1,000 meters. Now it's got so much heat out there, it's not losing so much. It's only losing 5 degrees. So you got a 5 degrees here, then another 5, which is -8, and that's the wet rate. So the wet rate is anything above the condensation. Dry rate to the condensation level. Dry to the condensation level, then all of a sudden you're into wet rate. As soon as you hit the condensation level, it's wet rate after that. So this amount could be 5 degrees, or 6 degrees, or 7 degrees, or 8 degrees, or 9 degrees, or 9.25 degrees. But it's going to be at a different rate than the dry rate. Stability of the air. Now what I did for you, okay, I'll proceed here. Because the last couple of sheets, I have them already written down, so you don't have to write them, because we don't have any classes left actually in this deal. So stability of the air. If given a choice, air would like to associate with air of the same temperature. Stable air resists vertical movement. So stable air, if you have air that they call stable, it has to be forced up. If it's where it likes to be, it wants to be there. Kind of, it's among friends. It doesn't want to go up. So it's got to be forced up. Stable air resists vertical movement. It doesn't want to go up. Unstable air ascends freely because of its buoyancy. It's lighter than the air around it. So it wants to rise. The environmental lapse rate is the average drop in temperature with increased altitude in the troposphere. That's where we are living and breathing. The adiabatic rate is cooling or warming of air caused when the air is allowed to expand or is compressed. It's pressure related. You need to know that the adiabatic rate is a pressure related deal. It either expands and cools, or it contracts, or is compressed and warms. Condition of the air, absolute stability, prevails when the environmental lapse rate is less than the wet adiabatic rate. The rising parts of air is cooler and heavier. So here we have a diagram. You have the dry rate, 10 degrees for, it loses 10 or gains depending on where you're going. The dry rate, 10 degrees Celsius per 1,000 meters. And you go up 2,000 meters and you get this place. And so at this point, you have condensation. That's the condensation level is right here at 2,000 meters. After that, in this case, this is 6 degrees. So go from 0 to -6, keep going up, -12, another 1,000 meters, another -6 to -18. So I'm going to focus probably the majority of this on what happens with the adiabatic rate. I'm not going to spend a lot of time with these things. In fact, I think I'll put this up. If Rebecca doesn't come in today, is she going to come in here today?
Yes.
Oh, she is?
Yeah.
Okay, then I'll do it later. Conditional stability occurs when moisture has a lapse rate between wet and dry adiabatic rates. I'm gonna evaluate this. Well, I need to go over this. But stable and conditionally stable air will not rise on their own. So you've got stable air and conditionally unstable, which means it can, they won't rise on their own. They need something to push them up. Stability determines the type of clouds it develops and whether precipitation will come as a light shower or a downpour. Okay? On occasions when stable air is forced aloft, there are things that go that we're going to get there in a second. On occasions when stable air is forced upward, the clouds that form are widespread and have little vertical thickness. So if I'm a cloud and I am forced upward, so I don't want to, I'm going, no, I don't want to go. And something is forcing me up anyway, the clouds that tend to form from that are thinner and widespread. They don't have a lot of vertical thickness. And precipitation is usually light. Clouds associated with unstable air are towering. So when you see towering clouds, those are clouds that want to go up. They delight in going up. These clouds were forced up there. They didn't want to be up there, but they were forced, so they're flat and thin. There may be light precipitation from them, not always, but there may be. These towering clouds are going to produce, if they produce downpour, they tend to be In fact, storm clouds are ones that are, you see clouds that are building fast. It means that these clouds are one to go at, have a lot of moisture in them. Stable and conditionally unstable air will not rise on their own. So this is the second time I've said this. Stable and conditionally unstable air will not rise on their own. I like that picture. They're going to need something to trigger vertical upward movement. So there are three things, mechanisms, chief mechanisms, that can do this force lifting, make these clouds go up. And these are the three. Well, there are four here, but basically convergent lifting, frontal lifting, and orographic lifting. Now, convergent is what you get in Florida. A lot of times you get wind coming both sides. You get some winds coming off the Gulf and off the Atlantic, and it comes together and it forces stuff up over the state. Where I live, or where I grew up, I don't live there now, I live here now, but where I grew up, you have mountains. You have mountain ranges on the coast, and so you have air coming off the ocean, and it's forced up the mountain. In Florida, there's not mountains. There are little hills. Sometimes this high, sometimes this high. It's flat. I wouldn't say that. So, but orographic lifting is where you've got wind that pushes the body of air. This is the little circles of body of air. And frontal lifting, that's when you've got a front. You've got a front that's pushing this air up. If it's a cold front, depends how steep it is. If it's really steep and it's a cold front, comes into a warm front, pushes air up, pushes it up strong and fast, and you get a lot of rain. And so I'm going to stop here, and then I want to talk about this next time.